In this video, we will apply and discuss the convolution principle on a simple first-order response type systems. There are many systems that can be presented by first-order differential equations. For example, a simple falling mass of a ball, a resistor capacitor circuit, the growth model of a population, or a heat transfer application using Newton's law of cooling, for example, or fluid-based analysis, such as the example that we will discuss today. If you recall, in a previous video, we have derived a water level control model using the conservation of mass balance equation with the help of the Poisson law. From the tank model shown, the system output normally arranged on the left-hand side of the equation, and the system input, which is normally shown on the right-hand side, is the volumetric flow rate. The convolution will allow us to find the corresponding output for any desired input if we have the impulse response of the system. So, if we have the impulse response of the system, simply by replacing the input by an impulse and find the output or the response of the system, then we will be able to find a corresponding output for any desired input using convolution. This first order differential equation would model the liquid tank height at time equals to 0 with an impulse function as an input as shown on the right hand side of the model. In mathematics, the impulse function is called the Dirac delta function, and this is the generalized function or distribution introduced by the physicist Paul Dirac. Please note, because of the water or liquid height h of t is 0 for t less than 0, the effect of the input, which is the impulse in this case, is to cause that height h of t to jump from 0 to 1 at time equal to 0. That is, at time of 0 plus, then the height will be equal to 1. And please also note that for positive values of t, i.e. for t greater than 0, the input, which is the Dirac delta function, is 0. And since we are interested in the unit impulse response for t greater than 0, then we should solve the following differential equation based on the first initial condition that the height at time 0 starts at 1. Remember that the general solution we have for this first order differential equation is in the form of c times exponential of minus kt, where c is the constant and k is the decay rate. We can easily find c using the initial condition we have, where the height at time 0 is equal to 1. This leads to a value of c equals to 1 as well, and the final impulse response is shown here. Now we have the unit impulse response of our system. Could we find the corresponding output for any given input using convolution? For example, what will be the output of our first order water tank level model if the input given is a rectangular pulse, i.e. if the input for our system, which is the volumetric flow rate, has a rectangular pulse looking form, what would be the response of our system? Before going over the convolution integral, let's first analyze the convolution as a sum of impulse responses. Now to do this, we can approximate the rectangular pulse input signal by a series of impulses as shown here. You may notice that the first and the last impulses are smaller than the value of 1 because they include the parts that are 0 before the pulse at time less than 0 and after the pulse at time greater than 1. Next, we simply plot the response of the system to each of these impulses as shown here. Then the result will be the plot as a sum of individual responses. And this zigzag line shown here is the approximate convolution result. To find the output of the water tank level system using the convolution integral with the impulse response h of t equals to exponential of -1 of t to the input shown in blue f of t, we will use the convolution integral shown here. Because the input function has 3 distinct regions, section 1, section 2, and section 3, we will need to split up the convolution integral into 3 parts. The convolution integral shown here means a reverse, shift, multiply, and add. The signal shown in green will be reversed. The integral limit is the actual shift, and you need to multiply what's inside the integral, and simply the integral is addition. So in other words, the impulse response will be reversed and then we will be shifting it, and as it overlaps with the input signal shown in blue, we will be multiplying the corresponding values and adding them at the same time. Okay, back to the convolution integral. Let's verify the results above using the convolution integral. As we mentioned before, because the input function shown in blue has 3 distinct regions or 3 sections, we will need to split up the convolution integral into 3 parts. Section 1 for t less than 0. For t less than 0, the argument of the impulse function t minus lambda is always negative. Hence, there will be no overlap between the reversed impulse response and the input function. So this means multiplication will always end up in 0. So the result of the first part of our solution is 0. Section 2 is for t between 0 and 1. Section 2 is defined when time interval is greater than 0 and less than 1. This is where our rectangular pulse input function has a value of 1. It is very important to note that the time interval is not the same as the convolution integral limit. The integral limit is defined by the pattern overlap. In section 2, this is the first pattern overlap we have. As shown graphically, the first pattern overlap is between 0 up to the value of t, where t is between 0 and 1. Hence, our convolution integral limit for section 2 will be between 0 and t. Evaluating the convolution integral for section 2, we get y of t equals to 1 minus exponential of minus t. Section 3 is valid when the time interval is greater than 1, and this is where our input pulse is 0. As shown graphically, the next overlap pattern shown is valid between 0 and 1, and this is what dictates our integral limit. Evaluating the convolution integral leads to the result of the third part of the solution. Which is e to the power of minus t into e minus 1. So combining the solutions from the 3 sections, we can get the complete answer for our convolution integral. As you can see here that the answer is an exact solution using the convolution integral as compared to the approximated method used before. In the next video, we will introduce Laplace transform, where such problems can be solved computationally in a much easier way.